I got interested in astronomy in the 2nd grade, got my first telescope in the 5th grade, well, half of it. My parents couldn't afford more than the tube, so I had it strapped to a stack tray for a year. Took 20 minutes to find the moon. I had to give up my security blanket to get the base of the telescope the next Christmas. So kept up with astronomy all the way through college. Started teaching astronomy at the college level as an undergraduate when Halley's Comet came along. So yeah, we got stuff going up there. Planetarium lecturer in Arizona during that time, moved to Oklahoma, chased tornadoes. Was a planetarium lecturer there for 10 years. Then I got hired by NASA to proof all the educational products they make. For 17 years, I made sure that everything is scientifically accurate and it was made for the right audience. Then in a little pandemic, I'm sure you missed the pandemic, it was in the news, but money shifted around in NASA and I was given 6 months warning that the grant was ending. And I now work up in Loveland at my kids' school. My daughter is a freshman, my son is a 2nd grader, and I teach technology, robotics, film school, college algebra, astronomy, meteorology, and tech for 6, 7, and 8 at school there. So I'm always creating curricula and having fun and doing that kind of stuff. I also have an observatory, little sister observatory to this one down in Longmont. Okay, so tonight's topic is black holes and the Oreo black hole. Secretly, I got you here just to talk a lot about black holes, but we're definitely going to cover the Oreo black hole. Whether there's some place inside of a black hole you could tuck a planet and have people happily live. So we'll answer that question. I love questions. You can do it anytime. You just go, shoot that arm up, I'll stop everything and take your question because I want you to get it when it's fresh in your mind. So what we're going to do is really briefly touch on these. Where's the idea of a black hole come from anyways? Can you make one? How do you do it? What are they? What do they do? How can we find them? Have we found any? And then finally, we're going to get into the frontiers of black hole science, including these Oreo black holes. All right, so who can tell me what a black hole is real quick? Yes. Go ahead. Oh, it sucks things up. That's good, yes. No? Okay. Oh, I was going to say, having worked for NASA, the reason this telescope isn't working is because they're using it to disclose aliens right now. So that's it. Yeah, just pull back the curtain. All right. To figure out where the idea of a black hole comes from, we have to figure out how weird space and time is. We are really used to the clock ticking along at 1 second, and I walk over here 10 feet, and I've walked 10 feet, and everything is fine. It isn't fine, really. Space and time is very, very weird. And it started, the first cracks in this understanding came from, little guy, again, you probably haven't heard of him either, Einstein. Einstein revised Newton's laws of motion and Newton's law of gravitation, and found that things are very different when you move close to the speed of light. So this came out in his watershed year of 2005. He also put out a paper on Brownian motion, randomness in molecules that helped determine that there were molecules, and the photoelectric effect. So the fact that you can have solar panels on your calculator or your house all comes from this too. So he was really firing on all cylinders this year. This also helped resolve some problems in electromagnetic theory that physicists went, well, it works, so we won't worry about that problem. So the whole idea of principle of relativity is that motion is relative, that it's really difficult to determine what now is when an event happens, especially if two observers are moving at different speeds. And the whole idea of special relativity actually comes from really simple algebra. This little triangle here, and just pretending that you have like a flash of lightning hit two trees at the same time, you could do it yourself. Just a little algebra. It's not very difficult to do. But before this, we just figured out, electromagnetic waves are special. Again, the equations work fine. if you're moving along and towing somebody and they throw a snowball forward, the snowball is going to go faster than if you throw the snowball backwards. That's our day-to-day experience. But that's not what special relativity leads us to believe. It's really bizarre. So time itself changes. If you decide that the speed of light is not going to ever change, the speed of light is always the speed of light no matter who looks at it, and that's what Einstein started with, then what has to give is time and space. So we're going to see that. So here's Amy and Beth, and Amy's going to sit here at Earth, and we're going to say Earth is not moving. It is. It's moving very fast. But we're going to pretend that the Earth is sitting still, and Beth is going to head out to Alpha Centauri. This is our closest star system, a little over 4 light years away. We can't see it from here, or we'd show it to you in the observatory. You have to go into the southern hemisphere. I think maybe from the Key West and from the big island of Hawaii, you can glimpse it briefly above the southern horizon. But Beth wants to go see it there. Just a little sci-fi link in. If anybody see the, I just lost it, Pandora, no, right. The planet's Pandora, Avatar movies. 2 Avatar movies. Avatar, okay. So they go to Pandora. Pandora is going around one of the stars, and it's a 3-star system thing. So that's the background plot line is all that movie is taking place over there. So Beth is going to go 4/5 the speed of light and head on out. Now it's going to take 5 years for Beth to get there and then turn around real quick and come straight back. So of course, Amy back on Earth sees 10 years go by. It's a 5-year trip. But because Beth went pretty close to the speed of light, it's only going to be 6 years on every possible measurement for Beth. Number of heartbeats, ticks of a clock, how many movies on Netflix she can watch. It's all going to be what you can fit in 6 years. It really is 6 years. And if you go a lot faster, closer to the speed of light, she might only feel a month go by going there and back, and still 10 years has gone by the time Amy gets to see Beth again. So this is called the twin paradox. Einstein said if you had 2 twins and they go out, one goes out near the speed of light and back, the one twin could be close to 100 years old, the other might have only had a week or 2 go by. That's what happens to the passage of time when you go really fast. So something between traveling over space and time is linked, but we don't know how deep yet. The other weird thing is, remember the snowball? Going along for you, throw a snowball out, throw it back, you can add the velocity, subtract the velocity, everything is fine. Well, if Beth decides to, coming back at half the speed of light, to fire a cannonball out the front of the ship, it's a little dangerous, but Beth lives that way. You would expect it to be a half plus a half the speed of light, right? No, if you do the math, it turns out that it's going 4/5 the speed of light. Velocities don't add correctly, not the way we are used to thinking of it. So combining 2 speeds is always going to be less than the speed of light. You can do your best to get to the speed of light, but you can never get there. It takes vastly more energy just to go a little bit closer, get up to 90%. You've used a lot of fuel. Go to 90.1%, you've used probably that much fuel again. Try to go from 99 to 99.9%, you may have to burn a couple stars worth of fuel out the back of your rocket ship. Try to go from 99.99 to 99.999, you may have to burn a galaxy through your rocket nozzle to get that little extra velocity. You just can't do it. Things with mass can't go to the speed of light. Photons do, anything without mass does, and photons do all the time. If you could go faster than the speed of light and you play with the mathematics, you would have a signal going back in time. You have all sorts of things in causality and what comes before what that get broken, and the information laws that I've talked about in earlier talks. You just can't do it. We don't see any evidence that particles or any other information goes faster than the speed of light. All right, so what about gravity? If we're going to get black holes, we've got to get a lot of gravity in here. So Newton said there's a force on the moon that points to where the Earth is right now. That's not true. Einstein said the moon can't know where the Earth is right now. The distance between the two make a time light travel of 1.3 seconds or so. So whatever the moon is feeling, where the Earth is, or vice versa, it's always 1.3 seconds in the past. And so they're not quite in sync. So we need a new theory of gravity. If Newton was right, and the moon and Earth instantly knew where each other were, then you could communicate faster than the speed of light. You can't. Gravity can only go at the speed of light too. That's a big leap. Once he had that, he was on to being able to come up with his theory of gravity. And as you can see, he became a world celebrity. And we still use his name, just synonymous with somebody who's really smart. So, very fast-moving objects or very dense objects both have very similar effects. Time slows down and space does weird things. So it took him 10 years to come up with now the general theory of relativity. Special just took care of velocity, left gravity out. General, kind of like G for gravity, brought gravity into the same thing. Again, if you have any questions, just shoot a hand up. So instead of a force pulling things down, what you have is gravity interacting with space-time as a material. You gotta think of space-time as a fabric, a substance basically. And the two are linked together. So where you have a lot of mass, you're gonna get a warping of space and time together. And so when an apple's falling, it's just traveling on the straightest line that it can in a curved space-time. I know, that's a big leap. That's a weird thing to think about. But the Earth going around the sun is going the straightest line it can in the curved well of the sun's mass right there. So let's take a look at humanity's approach to gravity all the way back to Aristotle. Aristotle said, an apple falling is just seeking its natural place toward the center of the universe, Earth. We kind of changed that and got the heliocentric model, but anyway. Newton came along and said, the Earth exerts a force pulling the apple downward. Einstein says the apple is moving along the straightest possible path through a curved space-time. So yeah, the Earth isn't that big. It's nothing close to a star or definitely a black hole. But there's a lot of curving space-time going on here right now. I don't have a slide for this, so I'm going to jump in with this thing right now. If Einstein never came along, nobody ever said the speed of light is going to stay constant and we're going to make everything else work around that. If that never happened, no physicists went this way. The first time we turned on the GPS system, it would have been great for a few days. And then we would have started seeing errors planet-wide. And then a few weeks later, you'd be off enough that, well, you don't really know which street you're supposed to turn on. And a month or two later, it'd be worthless. See, when you go close to the speed of light, time slows down. When you get close to a gravitational source, time slows down. Same thing. So the satellites up there are pretty far up. They're high above the atmosphere. They're feeling less gravity than you are in the room with your GPS on your phone. So time is running faster in the satellite than down here. And the way that GPS works is that they have extremely, extremely precise clocks. And they are listening to the radio signal coming from the different directions and different distances to the satellite, and they're calculating the error in the clocks. They need really good timekeeping. And so general relativity's equations would have had to have been plugged into them anyways to fix the GPS system. So we would have found it. We just would have gone, wow, why didn't anybody come with that earlier? All right. So some consequences of general relativity. How is the universe weird now that we have to deal with time and space being strange around gravity? Well, we can see why golf balls and bowling balls fall the same speed. There's probably an apocryphal or fake story about Newton going to the Tower of Pisa and dropping two things at the same time and people on the ground going, yeah, they hit at the same time. But it's true. If you get rid of air resistance, that little ball is going to feel the resistance of air a little different than that one. Take that out, put it in a vacuum. You can do a feather in a vacuum and a heavy ball in a vacuum, and they'll hit at the same time. They did it on the moon. They did a little experiment up there where you did have a great natural vacuum. So that's just those objects going the straightest possible line they can in a gravitational field. Our intuition goes, no, light things should go slower, but they don't. This one's a little complex, but this is where the scientific community really started to sit up and go, wow. There is a kind of a shifting of the orbit of Mercury that we can observe, making observations over years and decades of time. And Newton's predictions for how fast this shift should happen were wrong. As soon as scientists put general relativity's equations in, said what should be happening with Mercury, bingo, right on the spot. So it's going to be important why this is happening and what's happening with the sun and Mercury. It happens with all the planets, but Mercury is the easiest to observe this effect. All right, another one, and this is where Einstein, the rock star, happened, was he predicted that, well, light's going to bend too. Light's going to go the straightest path it can through a gravitational well. The biggest gravitational well that we have around us is the sun, but it's pretty bright. So what you need is to wait for the time for the sun to go off, and you can do experiments. Okay, that's not happening. It does, though, for a solar eclipse. For a solar eclipse from your right spot on the Earth, you do get to get rid of the sun, and you can see the stars around it. So Arthur Eddington went out and tested it. We found out that they tried to do this in the Chamberlain Observatory in Denver, but it was cloudy, so they couldn't do it. So they went to South Africa, set it up, took a picture of the stars around the sun, and came back, developed the film, measured how bent the stars looked, and it was perfect. And then, boom, Einstein was, boom. I didn't pay that to happen. He became a household name at that point. Well, there's other cool things that general relativity predicts that we've been able to see. We have an experiment called LIGO. There's a couple of these extremely long lasers, extremely sensitive, extremely isolated from things. Like just a truck driving on that mountain range over there will set off a signal here. They had to completely isolate it from all the vibrations of Earth, and they're able to pick up ripples in space-time itself. If space-time is a fabric and something shakes the fabric, the ripples are going to go through the fabric. And that's what general relativity says, and that's what we see. So we've been able to see close binary systems, we've been able to see neutron stars and black holes merge. That's a serious ripple. We've been able to watch, using radio telescopes, binary pulsars, neutron stars going around each other, and we can time them really accurately and see that they're very slowly slowing down and getting closer together. They're losing energy by making these ripples in space and time. And another consequence is the one we're here for tonight, are black holes. Objects so dense that not even light can escape. And this is just a diagram of how severe now we have bent space and time, that fabric. We've taken it off the map. So you have a little planet, not much of a dimple in space and time, a big old star, you got a pretty big dimple, but a black hole, you go down and there's no coming back out. All right, so how do we make these things? Let's talk about that. You need a bunch of gas and dust. and something makes that collapse and form a star. This is kind of where we are right now. Eventually that star runs out of its hydrogen, helium, or maybe a little heavier elements, and starts to swell up into what's called the red giant phase. That puffs off its atmosphere, makes a pretty nebula, and becomes a white dwarf. It's just a cinder of a stellar remain. Well, that's boring. Nobody wants to talk about cinders. So let's go the other direction and go really big stars. Get a really big star, it's going to go through a lot more elements, run out of fuel again. Everything's eventually going to run out of fuel. And you get a red supergiant, and then that eventually collapses, explodes. You get a supernova, pouring light and energy out into the universe. And the core gets smashed down into the black hole. Now, there's a little extra area in here where if the mass is just right, we're going to see it in just a second, you get a weird object called a neutron star, where we're not quite far enough to have it collapse off the map into a black hole, but all the electrons are mashed into all the protons. You just have a gigantic, supermassive atomic nucleus, basically, that's extraordinarily hot. So, in principle, anything could be turned into a black hole. You could take a mountain range and make it into a black hole that you wouldn't be able to see. If you put the whole Earth and smashed it into a black hole, it'd be about that big, ping pong ball or smaller size. That's some serious compression. But in nature, all we know is that you've got to have a big star and a big explosion to let this happen, unless you merge some other things. Like a couple of neutron stars get together, now you've gone over the cliff and you can make a black hole that way. But again, it all starts with the star. So everybody does ask, will our sun become a black hole? What do you think? No, it's too small. In another 5 billion years, it's going to do the planetary nebula puff thing. It'll swell up before then, swallow up Mercury and Venus. I think the jury's out whether the Earth is going to be swallowed, but it would definitely be melted into a big ball of lava floating in space. So no more mountain ranges, no more, just a big ball of lava. So, and then what's left over will be the white dwarf. So we don't have to worry about black holes here, unless they travel from someplace else. Another side question of this is, if something magically turned the sun into a black hole right now, nothing else happens, it's still the same mass, would we be sucked into it? No. No, we wouldn't. No. We would just keep going around once a year. It would get really cold. Global cooling, am I right? All right, so no sun, real cold. All right, so let's talk about black holes themselves. The actual idea of a black star or something that could have too much gravity that nothing could ever escape from goes all the way back to the 1700s. But it really never held, the math was wrong. So all we had was Newton's gravity and it just didn't make the correct predictions. But when we came along with general relativity, now someone could come up with a solution for this thing. Looking out in the world, up to recently, we had two main classifications of black holes. We had stellar mass black holes, so something big, not too much bigger than us, but 10, 100 times, something like that, range, blowing most of its material out, leaves behind a black hole. The other end of the spectrum, we have black holes in the center of galaxies that are massive, millions of stars, even billions of stars worth of matter inside them, gigantic things. And a big gap in between. Stuff around 100, 270 solar masses, we didn't have any examples of. So, real simple. There's not much you can say about a black hole. It doesn't have a lot of personality. It's got an event horizon. Anything outside can just zoom by. Anything goes in is doomed. It's gone. Can't come back out. Not easily. We can get into Hawking radiation and another talk. And information paradox, not right now. And then down in the center is this hypothetical singularity, this space-time point where everything is jammed in infinite density. Does anybody like the idea of infinite density? No, neither do the equations. So there's something else that's probably going on. We need a theory of quantum gravity to unravel this, and we don't have that. We have little hints on the edge of what might be the physics there. You have this horizon that surrounds a region in which nothing can escape. Radius is proportional to its mass, and for something that's just a few solar masses in size, the radius is only 3 kilometers or 1.86 miles. You could fit it inside a love balloon in Berthoud. Yeah, have you been inside Berthoud? Here's a picture of it in Manhattan. There's Central Park. That's the event horizon. That's not a solid thing. It's just the point of no return around the central point.
I have a question.
Yes, please.
You may be getting ready to answer this. Sorry.
Okay. Yeah, it's fine.
Put the cart before the horse.
That's all right.
So if something gets sucked into those black holes, where does it go? Is it just additional compression? Or
Yeah, it makes the black hole slightly bigger. Yeah, if you start throwing couches into this, it'll get a teeny bit bigger. Yeah. So it's directly proportional to the mass, linear. Yeah. Here's the sort of the anatomy from the outside of a black hole. Someplace in the middle, you've got a singularity. We don't really understand what's happening there. You got the event horizon, which is this point of no return. It's the point beyond which you're not going to see any more events. Events aren't happening out here. If you have some source of material to fall into it, like a star that it's in the same star system with, then it could be tearing off material from that if that star is now expanding itself and dumping stuff in. You've got a disk of material falling in, and it gets hotter and hotter towards the center because you've got a traffic jam. The stuff is getting in, but it's getting in the way of itself. It's heated up, there's pressure pushing it out. Some of that material gets funneled up and away around the outside. You get these jets out the poles of the spin axis of it, like that. Now, to compare this with a neutron star, I told you neutron stars are that little in-between area. These are small also. They exist in the 1.17 to 2.2 solar mass area. So below 1.17, white dwarf, above 2.2, black hole. So giving you a scale on that, I think this is this New York again? I think it is. Yeah. So neutron star is definitely bigger. It's not down there yet. So it's so easy to see if you get a couple of neutron stars to merge, you go all the way into black hole land. All right, so what do these things do? Well, they distort space-time. Talked about that a lot. Here's like a three-dimensional attempt to show space-time bending in around the Earth. They can bend space on a large scale. Well, the black hole in the center of large galaxies, big cluster of galaxies, bend space in a big way to, these are the nearby galaxies with big black holes in the center. All that mass is bending the light of distant galaxies back here in these little arcs. So you can see it's like a giant lens. Here's a nearby galaxy bending the light of a background galaxy all the way around it because it's almost perfectly behind it from our point of view. The black hole itself is a true hole in space. Anything that goes over the edge is gone. This is a diagram made by a computer, we're going to talk about this more in a moment, that shows the distortion of light paths. I'm going to break that down.
Okay.
Yes, question?
If a photon has no mass,
Yes.
how does a black hole eat light?
Okay, the light has to have a trajectory that would take it into the event horizon. Yep. So
only the light that is
its straight line distance happens to hit the event horizon. Yep. There is an area around a black hole where light can orbit and orbit infinitely. The straight line is a circle.
Does it get brighter?
Yeah, if you add more energy to it, more light comes in. It'll just keep building up. Yeah. Yeah. That's called the ergosphere. We'll see a picture of that in just a moment. So time dilation, I've mentioned, is as you get closer to the black hole, the flow of time stops compared to somebody sitting way out in the distance. At the event horizon, time stops from our point of view. Now there's an interesting paradox here, and you just got to put your head around this. I'm sitting here watching my friend fall into a black hole. I told him, no, don't go measure the black hole. And he went, no, I'm going to do it anyways. And he's going in, he's going in, he's going in. Seeing him flatten in the distance he's traveling, just like going very fast. And his clock is going slower and slower. The light coming from him is getting redder and redder. And somewhere just above the event horizon, I see him smeared into ripped apart particles of superheated stuff. It's a horrible way to go. What he sees, though, is he sees black hole come in, event horizon always out in front of him, always out in front of him, always out in front of him, always out. Oh, singularity is gone. He goes inside the black hole, from my point of view, and never knew where the event horizon was that I saw. And both are true. You just have to stick that in your head at the same time and go, I'm uncomfortable with this idea. But it's true. It's just the way black holes are. All right, so to show you why time slows and then stops, I'm going to give you a quick picture of your future. The ice cream cone on top is the only future you've got left. Sorry. The yellow is space, so I'm taking space from 3 dimensions down to 2 to make it simple. And time is flowing from the past down here into the future up here. The only place I can go in the future is in this cone, because if I go faster than this side or this side, I'm going faster than the speed of light. So Mars in 1 hour, let's see, no, let me change that. Mars in 10 minutes is outside here. There's no way I can get to Mars in 10 minutes or get a signal to Mars in 10 minutes. I certainly can't go there and brush my teeth in 10 minutes. So everything that you can't quite get to because of the speed of light limitation is on the elsewhere outside here. And you guys are sitting stationary relative to the Earth. Your future is just up here. You can't do anything about it. You're going to be in the future. An hour from now, you're going to be 1 hour older. A month from now, you're 1 month older. Nothing you can do about it. Time is ticking. All right. In a black hole, time and space tilt so that future cone tilts. And that future cone tilts so much that space and time change roles. Now your future is space. Your future is down. Your future is the singularity. And there's nothing you can do about it. 1 hour from now, you're 1 hour closer to the singularity. That's it, if it takes that long. But, guess theoretically, going side to side, you can go in time anywhere you want. There's not much exciting in the black hole an hour before and an hour after now. So it's kind of meaningless, but it is what's happening. So time and space change role because this tilts so much. Kind of crazy. Another thing that black holes do, at least the smaller ones, if you're trying to get there, is spaghettification. Right now, your head is probably 1/millionth of a gram lighter than your feet per cubic something, just because your feet are closer to the center of gravity of the Earth. You guys are tough enough to take that, right? That doesn't hurt you. But as you get closer to this stellar mass black hole, eventually your head is 10 pounds lighter than your feet, and then 100 pounds lighter than your feet, then 1,000, then 1,000,000, then 1,000,000,000 pounds lighter than your feet. You don't stand a chance. It's really ugly. So yes, as you get closer to a stellar-sized black hole, you get tidally ripped apart right down to the atoms. So yuck. And then, of course, right down in the center is the singularity, and we really don't know what's happening there. And Einstein's equations fail too, because you get infinities. So this is all great. This is all mathematical. I've just played with equations so far. How do we find these things? How do we know if there's anything out there? All right. Well, we can see it through their interaction with other things. If there's a black hole with a star, they obviously are going around, each other, and we can tell just using Newton's laws or using Kepler's laws even, how heavy the two things are. That's kind of nice. The most famous example, and first one, is Cygnus X1. It's about 8,000 light years away. And I'm going to show a picture of it in just a second. We think there's probably about 100 million black holes in our galaxy wandering around. We know of about 17 to 20 for sure. So how do we know? Okay.
How did we get from 17 to 20 to several million?
It's just the estimate based on this lifetime of stars. The bigger stars that make black holes have very short lives. And so we can see how many generations of that those have happened. So, all right, so someplace in there is a black hole. Can someone point it out to me? Right there? Okay, yeah, black hole. All right, little small joke, very small joke. So the first candidate is Cygnus X1, and it is in the star system right there. But I can't see it. What we need are different eyes. So we've put up other things in orbit, like the Chandra X-ray Observatory. To help hunt for these things, you need X-ray vision. So if you start with one of those big stars that's starting to become a supergiant, and it happens to be orbiting with a black hole, then there's a center of mass of the system. Half of the mass is on this side, half of the mass is on this side. It's all in a little black hole, maybe close to a singularity. Everything in this little bit right here down is now towards the black hole. So it falls in. And then it forms that disk that gets heated up so high that you're getting tremendous amount of X-ray radiation out. So if you find lots of X-ray sources, you got your black holes you're looking at. We can see black holes being born when supernovae go off. We have the Swift Space Telescope looking for flashes of gamma ray bursts, which are even more energetic than X-rays. In the center of our galaxy, we have Sagittarius A star. That's how you say it. It's an asterisk, but we don't say asterisk. It's a giant black hole, millions of stars, our sun's worth of mass in it. We can time the stars nearby and see that they're whipping around something, but it's dark and small, so it matches our idea of a black hole. So going back to this simulation, and could I get someone ready to kill the lights for a second? So this is simulation. This was made for the movie Interstellar. This is what the general relativity equations create. And what they did is they went to Hollywood. Nolan went to astrophysicists and said, "Do you have a picture of these things?" And they said, "Well, not really. We've got diagrams." They said, "Can you teach my special effects folks how to put these equations in?" And they got, I don't know, hundreds, thousands of high-end NVIDIA cards and cranked up the mathematics on it and came up with an animation. So that is what approaching a black hole, taking a look at what you would see with just a flat disk of material around it. That's all it is, just a flat disk. It's that accretion disk coming from a neighboring star. All right, you can bring the lights back up. So let me break this down. So the black hole shadow is obviously the thing in the center. This is the disk, accretion disk. This is the warped, by gravity, bending space-time like a lens. This is the top of the back of the disk. This is the underside of the back of the disk. This little ring, the photon ring, is the echo of the earlier rings after the light has gone around the black hole 3, 4, 5, 6 times. This side is brighter because it's coming towards you. It's Doppler shifted towards you. This is dimmer and redder since it's traveling away from you. So that's cool. We know what they should look like, but have we tried to get a picture of some? Yes, we have, yeah. We've got something called the Event Horizon Telescope. It's a compilation of telescopes using the entire size of the Earth to make images. Now, this is the second image that they took. This is the picture of Sagittarius A star's environment. And we see the bright spot, and we see a hint of the disk and the reflection underneath. This is an actual image of the area around our galaxy's central black hole. There's a bigger black hole around a galaxy M87, and M87 is a relatively nearby galaxy with just a giant black hole. This is actually the first image. Then they went back and got fancy with it, and they figured out the polarization. So polarized sunglasses work by getting rid of light going only one direction instead of the other direction. This is the magnetic field. The electrical properties of the black hole are changing how the inflowing gas works. So that's pretty incredible. That's really recent. 2019, that was issued. And the day that it happened, I made that my screen on my phone. And I haven't changed it since, even though I've got lots of cute kid pictures. Other things that show where black holes are, just the pull of gravity on nearby objects. We know that most, if not all, galaxies have supermassive black holes in the center. We can see that, remember, the magnetic fields can take the inflowing traffic jam of material and throw it out the north and south poles off into space. If we look in our X-ray eyes, we can see these jets coming out of galaxies, intergalactic jets of material as these things gobble stars, and some of it burps out the ends. We can also see gravitational waves, like I said earlier. When two black holes merge, boom, that makes a huge ripple in space-time. We're going to try to put one in space called LISA, launched in 2037, but if the writers and actors strike keeps going, that could be pushed later. I'm kidding.
Endless, gravity, items just hit.
We have, yeah, with LIGO, we have seen two black holes merge and then ring down. This is the warping of space-time through Earth. This hit Earth in 2015 or 14, something like that. So if you were alive then, this ripple went through your body, went through the whole Earth. And you can see the rippling of space-time, and then the space-time jittered violently. Now, the amount of jitter, smaller than the diameter of a single atom. But we're able to detect that. So, all right, a little more on black hole physics. We were trying to figure out what's happening in the singularity. Stephen Hawking got famous for figuring out that right at that edge of the black hole, if you mix in quantum mechanics, there is a reason that a little energy does escape. A little positive energy comes out. It's based on virtual particles, and I'm not going to say more. And negative energy goes in. So over very long periods of time, like a small stellar mass black hole, 10 to the 200 years from now, that's a one with 200 zeros after it, will eventually evaporate. So we will eventually get the energy back out into the universe, but very, very, very long time. The temperature of a stellar mass black hole is 10 to the minus 6 Kelvin. So the whole universe right now is about 2.7 degrees. So the whole universe is too hot for these things to start shrinking. They're still growing just based on the temperature of the universe itself right now. And that will be the case for a very, very long time. All right, so let's get to the frontiers. We are just about to the Oreo portion now. We're wrapping it up. Some of the things we wonder about, like, why don't we see these mid-sized black holes? 10, 80, 140 stellar masses. We're looking for them, but maybe in a system where you've got another star to help us see it, you're just not going to have that process happen easily. It's going to take out the other star too. And without something feeding a black hole, it's real hard to detect them, just like my black slide earlier. But with these mergers that we are measuring at LIGO, GW190521, rolls right off the tongue, showed that a black hole about 85 of our suns in mass merged with a 66 solar mass one, making one that's about 140 solar masses. So we finally got one. We got a couple that were close enough together and they merged. We think maybe medium-sized black holes could have come from two giant stars merging. You get some really big stars. They live very short lives and enter the black hole phase pretty fast. People have speculated that black holes might lead to portals to other parts of the universe or other universes, or they might be big bangs inside them that create another universe. We don't see evidence of that. We don't really know, but it's probably not that way. To get a wormhole, you actually need something called negative mass, and we haven't seen that come out of any experiments yet. So we probably don't have tubes connecting other universes like that. Probably not. So the question is, that we actually came here for with the Oreo black holes, is can a civilization exist inside a black hole? What happens inside? Could there be a white center? The answer is yes, but here we go. So, what's inside? We really don't know. We could just have nothingness down to a singularity, or maybe frozen quantum space-time fuzzy stuff, or maybe the singularity can only get so small and it's actually got a extended region inside. We just need a theory of quantum gravity to figure it out. Second, if you're going to go in the black hole, I already said that your fate is the center, right? Your future is down. So that's not good. That makes it a one-way trip. But if you want to be a civilization that lives inside of a black hole, you just need to be picky about the size of the black hole you're going into. You don't want to be spaghettified, so the little ones are not going to work. You need to have a supermassive black hole. The ones that are in the center of the biggest galaxies are gentle. You can actually walk or float up to the event horizon and gently go beyond it, say goodbye to the world, everybody sees you vanish. You don't get ripped apart. It's okay. All right, that's nice. But from there, after that, you want to stay away from the center. There's still going to be tremendous tidal forces way down in the middle somehow. Black holes get bigger linearly with mass, so get enough of these growing, you can get close to the edge, stay close to the edge, and you won't get torn apart by the stuff happening further down inside. If it's all empty and you just have a singularity or fuzzy singularity down there. So you don't want those tidal forces. Alien species might be tougher than us. Maybe they can take some tugging and pulling. Creatures in the bottom of our ocean can take care of pressures and conditions that are very bad for humans. All right, so how do you stay near the edge? Well, general relativity says there's only one way down, but didn't say this earlier, that's for a black hole that isn't spinning and doesn't have an electric charge. Well, M87 does, it has an electric charge. We saw the little lines in the accretion disk of strong magnetic fields. So probably all black holes have charge and all black holes are spinning very, very fast. So the only things you can know about a black hole are its mass, gravity, its electric charge, what kind of electric field it has around it, and how fast it's spinning. And this comes from something called frame dragging. Okay, can you picture putting your hand in the swimming pool and then swimming your hand around in a circle? What happens to the water? The water starts spinning with you, right? Space-time is a fabric. If you've got a spinning black hole, space-time is going to spin with it too and start speeding up. So that's the term, black holes have no hair, saying there's nothing else that you can talk about in a feature about a black hole. So spinning black holes drag the frame around them. That Mercury orbit precession I talked about earlier, that's frame dragging from the sun. We put a space probe over around Earth called Gravity Probe B with the most perfect sphere inside ever created by humanity, and got that spinning, and we're able to measure this slight variations of its function and show that we have frame dragging in satellites right around Earth. Newton doesn't say that happens, but Einstein predicted it, and he was right. So here are the incoming lines that should be straight, and they're just wrapping up around the black hole as it spins. There's another picture of frame dragging using our grid idea of space. All right, so you can go even further into the fun here. You could actually theoretically rip a black hole apart if you could convert its gravitational energy into spin. If you could turn it back on itself, you could spin it fast enough to get the event horizon to tear away and see the singularity inside. That's called a naked singularity. We don't have the technology for it, but it's theoretically possible. Another way to do that would be to continue to drop things into it, the black hole, in just the right way to keep spinning it up faster and faster. And what happens is not every path inside the black hole ends up in the singularity. You actually get all sorts of potential stable orbits inside the black hole. Here's some diagrams of them. They can be really weird. They can be spiral patterns, roller coaster things, figure eights. So your planet in here just has to be in one of those stable spinning black hole orbits, and it can stay there forever until the black hole's gone, and avoiding that singularity down in the middle. So rotating black holes, this is the ergosphere I said earlier, have an area around them where the light is in permanent orbit. That's inside this kind of pinky orangey color. And if you ever want to solve the energy crisis, just get your advanced civilization technology to dip into that, and you can get energy from the black hole to your heart's content. You can power all the planets in the empire. So, another way to create stable areas inside the black hole is to just go get a lot of electrons and keep throwing them in. Give the black hole a stronger and stronger electric charge. And so you get additional stable orbits inside. Your planet just has to be opposite charge, same charge, and same charges repel, and you don't end up in the singularity. So if you have spin and charge, you get more stable orbits, but that doesn't give us a place to actually visit. Could life begin and survive in there? Well, if you could get a planet in there on one of those orbits and keep it away from the singularity, you've got a place for them to be. Now, how do you power this? You don't have a sun nearby, right? We love sunlight. We need that for life. So where do we get our energy for the civilization? Well, if you are on that planet looking up away from the singularity, you actually see the whole universe. It kind of looks like it's coming at you through a little tunnel in the darkness. But every place, all the way around the black hole, all that light is coming in. It's really distorted on the edge, but it's kind of normal in the middle. So you're getting some energy from the outside world. If there's a big star nearby, then you've got some starlight coming in. So that would be great. Astronomers looking out there could kind of figure out what's going on eventually. Now the black hole could be spinning a million times a second, so you got a blur going by here. But, get high-speed photography going, start going, hey, I think there's something out that hole in the sky. So that's one interesting way. Another energy source would be tidal forces. It's going on weird trips around the singularity. The planets could be squeezed and tugged in different directions. We get a little bit of that effect from the sun and the moon, but the places in our solar system where we see a lot of internal tidal heating is the moons of Europa and Io, Jupiter, and the other ones too, but these are really quite pronounced, and Enceladus around Saturn. In fact, we are looking to see if subsurface oceans underneath these crusts of ice might have life in them, and NASA's working to do experiments by that. One of the early proposals was to fly out there, drop a nuclear bomb, blow a crater, and take some samples. Let's not do that. That's probably a bad idea. So tidal squeezing of this planet could give them geothermal energy. Keep a ocean melted from below and like that. All right, so if we do have enough energy now to keep our civilization going, they're not getting crushed by the singularity, what would they see looking through this tube into the universe? Well, time outside the black hole is racing forward at an unbelievable speed. They could probably even see galaxies moving and changing and morphing. From our point of view, well, they can't say hi to us because they're inside of a black hole, nothing comes out. And they may not exist in our time for hundreds of billions of years. And by that time, galaxies are going to start running out of new stuff to turn into stars, and the universe is going to be going dark. But they're just going to get started at that time. All right, that's what I got. Any questions? Yes.
You just click back to the slide with the diagram describing the different parts of the black hole?
Sure.
I'm curious because we were discussing, with astronomer who is falling into singularity at whatever rate, they'll only be able to see the rest of the galaxy, the rest of the universe through a tunnel. Would they not be able to see the accretion disk? Would they already be too far into the singularity?
Oh, no, they would see the accretion disk. I was just going by a black hole sitting out in space because accretion disks are really hot. Kind of a little extra danger there. So, let's see where. That was way back. Oh. Yeah. Okay. You got it. Other questions? Yes.
The illustrations and drawings trying to explain Einstein-Rosen bridge
Mm-hmm.
show two black holes connected. So we can think of that, okay, there's a doorway. We jump in this black hole and we spit out that black hole. Except black holes always pull in.
Right.
I'm going to jump in this one and we spit out that one.
Right.
You mentioned a couple minutes about Einstein-Rosen bridge.
Yeah, I don't think I've looked at it too closely recently, but are you talking about the same physics that was done for the book Contact?
Well, I mean, the illustration shows there's two black holes connected, but really it's more like a wormhole.
Right. So, yeah, with wormholes, what I could best speak to is contact. So, Carl Sagan went to black hole researchers, I think Kip Thorne was one of them or something like that, and said, all right, I need a mechanism for my book where aliens can travel a great distance very quickly. And is there a way to do wormholes that way? Like I said, with the black hole, it's a one-way trip. So they did come up with the mathematics of it, and it is supported by general relativity that you can have these connecting tubes between two locations in space. One element that we don't have is that negative mass to keep it open. Also, working the equations, if I remember correctly, yes, you could do it and hop to the other side. The other is, as you enter, all the light and energy that has gone in the tube ahead of you blasts you with gamma ray radiation and you're cooked. So you see a glimpse of the other side, then you're vaporized. But another problem with wormholes is relative motion of the two ends. They become time machines, and that is a problem too. So can I do the concept of now real quick, just for a moment? All right, so here I am. Here's my now. I'm going to pretend that the Earth is not moving, and I'm going to look out, and someplace across the universe in another galaxy, there happens to be another planet that's exactly not moving with respect to us. And there's an alien sitting there reading the newspaper. Okay. If I start walking towards the alien, my now and that alien's now change. Now, because I picked a huge distance, just walking speed throws our nows so out of sync that I'm probably 100 years in his future now. So my now is the alien reading the newspaper over there is the great descendant of that alien. Now, if I back up, now it's that alien's great-great-grandparent that's reading the newspaper right now. So just a little motion at great distance And that's based on special relativity. That's not even general, that's just special relativity. So if you have a wormhole and one side is drifting, either towards or away from this mouth, then it's going to be taking you forward and backward in time because you just popped over instantly. You just did the experiment, the thought experiment that I just created. And so, as far as we know, time travel backwards creates paradoxes, and we just don't see a mechanism to do that. So I did give a big talk on time travel in fiction and fact years back. All these are, most of the talk up to this year, talks for like about the last 8 years, I think are all on YouTube. So if you do want to explore some, all of the speakers we have digitized there. So. All right, kind of weird, huh? Special relativity is not our intuition, but our intuition is made for people not moving very fast at a nice, comfortable temperature, very low pressure, and like that. When you get into vast sizes of the universe or subatomic scales, the universe doesn't match our intuition. When you talk about temperatures of the center of a star or temperatures near zero, matter just acts completely unlike what we expect. We have an intuition based on what the surface of the Earth is. And it takes careful observation and getting over your preconceptions for scientists to tease out how weird the world is, universe is. Okay. Any other questions? Yes?
Weird one, but could you theoretically have accretion take place inside the event horizon, but away from the singularity if it was a large enough black hole? So like,
Yeah, if you have those stable orbits in there and matter's falling into that orbit, absolutely. Yeah, you could. I hadn't thought of that, but yeah, you could. I envision ribbons of hot plasmic death circling around, and it would be very pretty, but very deadly. So yeah, that would be really bad if that civilization's going along great and a star wands in and gets captured in a black hole and then starts feeding its material, and suddenly everything becomes death. So yeah, gruesome again. So, all right. Any other thoughts?
Can a black hole contain multiple singularities?
No, but a rapidly rotating black hole can form a toroidal singularity. So you have a donut instead of a point. I've seen the math on that. So, yeah. But again, we're speculating whether the physics is really holding up in there. So you're pushing beyond where general relativity works. It's Newton only went so far, and when we started getting really high velocities, it fell apart. When we got really high amounts of gravity, it fell apart. But now we're pushing it close to a point of infinity, and it falls apart again. So we still need another better, more complete theory. And just like if you simplify general relativity by lowering the velocities, it pops back into Newton's equations. It's fine. So what we just need to do is be able to go from that 99 the rest of the way, and general relativity can't take us there. So. Okay, good. All right, how's the telescope stuff?
Mark's going to get to run it, so thank you again, John.
Thank you. Thank you all for coming. Thank you for being the biggest crowd since February 2020.